Okay, now, we're finishing up this chapter here dealing with rates. And one of the big things that we can get from all this information is something called a rate mechanism. Now, this is a big thing in organic chemistry. I used to teach organic chemistry at Palmer College. And this was an area that helped people understand why reactions work the way they do. We're not going to get into this too heavily, but we're going to get into the verbiage of it. We are going to get into a bit of the simpler aspects of it, so you can see that what we take for granted is something where we have reactants, they collide, you get products at the end, is actually more complex than that, particularly when you get into organic chemistry. We find that sometimes when things collide, you get these new products, but one of these products turns on to recollide with something else that was one of the reactants. And then you get these new products, and then one of the things that was created is now part of something new that's been created. So we have to be able to look at all the various steps of the reaction. Sometimes there's as many as 5 steps. Most of them are like 2 or 3 steps. So the best way to think of this is, let's suppose that you decide to go on a Christmas shopping trip. You're going to go to Chicago to Michigan Avenue, known as the Miracle Mile, and just gorgeous setting for stores and buildings that are open that you do your shopping in. It's just, if you like crowds, this is the mecca of shopping right here. Okay? Now, I realize that now this is not a good time to talk about this being COVID out there and everything, but still, you know, you're still looking at them maybe down in the future. So let's say that we are not dealing with COVID issues, that we are now going to go shopping in Chicago. Yay us. So you decide to meet your friends over at the Shell station in Hillsdale, and then you get on I-88 and you go all the way to I-88 until you hit I-294, better known as the Indianapolis 500 Raceway, Chicago style. And then you take that and go all the way through to downtown. You get off on Lakeshore Drive, take Lakeshore Drive up to a garage near Michigan Avenue, and then you're set to go with your shopping trip. It's also say that you have friends that you're meeting there, and you're trying to coordinate times. And let's say that that specific time is why you plan to leave when you plan to leave. So you have 3 steps of this reaction. I-88, where you go, in theory, 70 miles per hour. I-294, which is, they think that people who drive 70 are quaint people. They're crazy. And then you get to Lakeshore Drive, where it's bumper to bumper traffic. And you're lucky you can get, to the next stoplight within a handful of minutes. Now, of those 3 steps, which one is most likely to make you late? In other words, if you mistimed something or something came up, which one of those 3 steps would be the issue? Well, the I-88, this is winter time. They're not doing any kind of road work unless there's something horrible that's happened recently. But there's going to be no road work, so it's just a clear path to I-294. Get to I-294, you're not even going to see police there because they're scared to be on I-294, and so people are just going crazy on that. So that's as fast as you can possibly go. Lakeshore Drive is really, really slow, painfully slow. And if you were to try to get from point A to point B, there's a lot of issues that can crop up to cause you to be delayed and delayed and delayed. So when you plan a trip like that, you don't plan on anything happening in the first 2 steps. The 3rd step, you have to anticipate issues, and in order to get there on time, you have to work around that. So the slowest part of your 3 steps is what we would call in chemistry the rate determining step. All right. So if you have a couple of reactions causing an overall reaction. If one is fast, the other is slow. The slow one is going to determine how fast that reaction goes. It's kind of like the theory of the weakest link. A chain is only as strong as its weakest link. A trip is only planned properly as long as you plan for its weakest part, or the slowest part. Okay, so that's what we're dealing with here. Now, those particular reactions that we are talking about that make up the multiple steps of an overall chemical reaction is called an elementary reaction. An elementary reaction means exactly that. It is the simplest of all the reactions. They're all one-step reactions. And so you're going to have multiple one-step reactions that are going to allow us to create this new compound. So let's take a look at an elementary reaction to start with, and then we'll build up to a multi-step reaction. Ozone, which is O3, reacts with nitrous oxide, or nitric oxide, I'm sorry, to produce oxygen, or what we call elemental oxygen, and nitrogen dioxide. Okay? And so let me put that over here, O3. And I'll put the phases in here. It's not necessary, but it just kind of grinds against me when I don't write it in there. But for the sake of speed, I didn't put it in the equation and script. So this is what we're looking at. We call this an elementary reaction because this is it. These two collide to create these two products. The end. Okay? Now, when you have an elementary reaction like this, then something rather different happens. And what I mean by that is that when we did those problems, when we were trying to find rate laws, like we were trying to find the rate law here, R equals K times the concentration of O3, the M power times the concentration of NO to the N power. We weren't sure how we were going to get it because we knew that, we knew the people who put the problems down knew that these were not elementary reactions. And so we had to check to see the data of experiments run where you're looking at the rate versus the changes in concentration, and that's how we came up with the M and N. And sometimes the coefficients of the equation matched up and sometimes they did not. Well, elementary reactions, the coefficients will match up. You don't have to go through those experiments. If you trust that the people who tell you this is an elementary reaction are telling you the truth. And what's worse than fake science? The sky's falling. So, we have coefficients here, even though there's no numbers written here. We have a 1 here for the O3 and a 1 for the NO. And those become exponents here, just like we've seen before. So we're going to replace these with 1. So the rate law for this is going to be R equals K times the concentration of O3 times the concentration of NO. That's it. That's all there is to it. So whatever the coefficients are, they become the exponents of our values right here. Okay? All right. Let's take a look at the second example. The second example, oh, yes. One more comment, I almost forgot here. Because we have two molecules involved in the reactants of this reaction here, then we say that there's something called a molecularity. And a molecularity is a word describing how many molecules were involved in the collisions in the reactants. And since we have here two molecules, the molecularity is based upon the number 2. It isn't 2, but it's based upon the number 2. It's a word, and the word we use for that is bimolecular. If we end up with one molecule 2 gives us the bimolecular. We have a word for that, and that is unimolecular. Now those two are extremely common. In fact, I'd be willing to bet that makes up about 99% of all reactions. Now it is possible to have 3 molecules involved in the collisions, although, like I said, it's pretty rare. We call this termolecular. Now, I giggle every time I put down termolecular because visions of 13-year-old boys hearing that, just giggling all to the side, gives me a pause to say that I haven't really totally grown up. But anyway, so that is an important distinction in the types of elementary reactions that you have.